developing two major mass spectroscopy and electron spectrometry system in-house. He is also a principal investigator for three major payload activities at Indian Institute of Space Science and Technology, including plasma measurement instrumentation payload around Earth, Mars, and Venus. He is an avid educator with a keen interest in disseminating scientific theory and ideas among a wider reach of student community and public. With this brief introduction, I welcome you, sir, for delivering the lecture. Over to you, sir.
Good afternoon. Can you hear me?
Yes, sir.
Okay. Thank you very much for your nice introduction, and thank you for your invitation for the program. I'll be presenting an interdisciplinary work which was done at IIST, and that is just the beginning of our activity in the space science and technology. It was our first mission to space from IISc. So I'll describe to you a little bit of history, how we started this activity and how we are going ahead with it now. So though I present this work, this is done by many people together, many faculty and students were working together. At some point I'll show you their name pictures also. So, hello. So I'm going to talk about this mission. It was named as ARIS, Advanced Retarding Potential Retarding. Hello. So the name of the mission is Advanced Retarding Potential Analyzer for Ionospheric Studies. So I'll just give you the background. Mainly, our atomic and molecular physics research at IIST is focused at molecular physics, ion molecule collisions, electron impact, etc. We also support some electric propulsion research activity. We are also building spaceborne sensors and also cold atom-based sensors for space application. So this is a spectrum of activity. The main strength of our activity lies in our ability to develop instrumentation. So I'll focus only on that today. Fundamentally, our interest is to understand how high energy radiation interacts with matter. This is where the story starts. So the main thing is we were studying how, and we are still studying how very high energy extreme UV radiation or fast charged particle radiation interacts with molecules, particularly organic molecules, in general all types of molecules, and how the energy deposition mechanism works, and after that what happens to these molecules. This has significance, as you are all aware, that our atmospheric processes are driven largely by the radiation flux which we receive from our sun. A lot of interesting things it does at different levels, but our particular interest is in the process of ionization and excitation. So obviously I'll be talking about ionosphere. This has a lot of interesting implications. I will not be spending too much time on that today, but if anybody is interested, we can discuss. So this is our core capability. We build our own instruments. They look messy. This was not what was launched in space. You can't launch such things in space. That I will show you. But these are the instruments where we basically study how high energy radiation interacts with matter. So the setup which you see on the left hand side, it has very special capability. At present, it's the only instrument with that capability in the world. Right hand side setup is actually for electron impact. On the left hand side setup, we actually study using this tunable laser. We actually study the excitation properties of molecules in this instrument. And on the right hand side, we have instrument where we do electron impact experiments. Again, I will not be talking about the details of these instruments, just to demonstrate that we build our instruments ourselves. So we have certain expertise. I'll quickly bring you to the subject of interest today. I do not know how many of you can recognize these photographs. Anybody would like to recognize? I don't know if I can see the chat in this mode. Just a minute. The pictures I am showing here, the top, this picture, let me again, can you see my full screen mode?
Sir. Yes, sir.
Yeah.
Yes.
Yeah. Okay. So this picture is Triton. It's one of the moons in our solar system. This picture is Pluto. This picture is Titan. This is Triton. This is Titan. Titan is the moon of Saturn. Pluto, you can, depending upon your interest, you can call it planet, dwarf planet, non-planet, whatever. Now you see these objects, they are very colorful, and these are only few, there are many others I'm not showing. And these, the reason why I show these three is basically, first, they have a solid surface. So if you ever go there, you can actually land on them. Then they have an atmosphere around them, and again, these are not the only objects having atmosphere around them. There are many objects in our solar system which have atmosphere. But one of the densest atmosphere is in Titan. If you land on Titan, and this on the right hand side here is an actual picture which was taken by Cassini-Huygens lander. This is a Huygens lander which has taken this picture, landed on Titan. That is the moon of Saturn. And what you see there is this bluish haze, yellowish haze. This haze is actually very high density of aerosols. Then, of course, there are questions how these things are formed. And you work in atmospheric sciences, you know this can form by several mechanisms of aggregation. So the puzzle was, what are the aggregation mechanisms which are forming this, and how they are formed. And these kind of haze or aerosols are not exclusive to Titan. This is the picture of Titan again. This is just to show you how the haze is surrounding the planet, surrounding the moon. This picture is picture of Pluto, and you can see there is haze around it as well. This is Neptune, and there also you can see this is false color image. These are true color images, by the way. This is false color image, and you can see there is haze there also. Haze is, these are all aggregates of molecules. Question is how they are formed and what are the processes which are responsible for it. And obviously these three examples, and there are many others where the temperatures are quite low. But some process has to start this. So there are several models which are being tried. But obviously, as you are aware, all these models depend on the radiation, particularly the high energy radiation, which is received from sun. Mostly that is driving this dynamics. Okay, so why we are interested as atomic and molecular physics people, why we are interested in this? That is because, I come back to this, you see this red material here on Pluto, the same red material here, and actually this bluish particulate material here. These are all organic molecules. They are not found on Earth. They are only found on these systems. And these are not the only systems. They are found on asteroids. They are found on comets already experimentally. In situ, people have detected these objects. These molecules, they are named as tholins. We don't know their exact structure. Their composition is there are many different ways in which they can be formed. The puzzle still stays how they are formed. We don't understand them. People are trying to create them in the lab, but they are formed in these surfaces. The question again is how they are formed, why they are formed. Does it have anything to do with the high energy radiation which we receive from sun? So all these things point to one thing. If you have a planet and a solar radiation is coming towards you, this solar radiation not only contains electromagnetic radiation, it contains high energy electrons and protons and other heavy particles, mostly protons, but other heavy ions also. And these radiation particles, if it is electromagnetic radiation, it is hardly affected by the magnetic field of the planet, but the charged particle radiation, obviously, as you know, gets affected by the magnetic field of the planet. And then these high energy particles, charged particles particularly, can get trapped in these magnetic field lines because, as you know, that the charged particles try to go around the magnetic field. So they can get trapped around this planet, just like our Earth. Also, we have this kind of magnetic field driven storage of high energy radiation, charged particle radiation. And obviously, this is also, this supplements the processes which actually happen in the upper atmosphere, in Earth's upper atmosphere also. So then question comes is that, okay, what if I have a sheath of charged particles here, what can it do? The first and important thing which it does is it forms, because the pressure here are very low, the atmospheric pressure is very low there. We are talking about something like 1,000 kilometers height. But at the same time, the volume is very large. So even though the pressures are very low, since the volume is very large, you can still have a thermal condition, a situation like a thermal condition. And when you produce large number of ions and electrons, they can easily get thermalized and you actually form a plasma, a low density plasma. So the ionospheres are generally characterized by plasma. So there is a large amount of plasma present there with varying density of ions and electrons, which are again related by the process which is driving them. For example, if you are facing the sun, you obviously expect the plasma temperatures to be high, and here and on the back side, you expect the plasma temperatures to be low. I will show you some of our measurements, what happens around Earth at the end of the presentation. Okay, so now one wants to study this. One has to go there, because these signatures don't all the way come down to Earth's surface. So typically you have to go between 300 to 1,000 kilometers orbit to do any substantial plasma measurement. So you have to target a lower Earth orbit. So when we launch spacecrafts, different orbits are targeted. Generally an orbit below say 400 kilometers is not very practical because of the air drag. You can do experiments, but short-term experiments. Once you go above that, you can have stable orbits and several months or several years of orbits. So we also wanted to do such experimental measurement, first around Earth, and then we hope to do same things, same kind of experiments around other planets too. So we want to understand this process. We have to first design an instrument which can handle these kind of temperatures, ions and electron densities. It should survive this plasma, and not only survive, it should also measure these plasma conditions. So I will just quickly tell you what we mean by these plasma conditions. Okay, so I'll list quickly what we have achieved so far and what we can achieve so far. So we use a device, it's called retarding potential analyzer. I will explain to you what that instrument is. And the whole payload is like 4 kilograms. It consumes less than 10 watts of power, and the box is about this size. We can detect charged particles of ionic form from 0 to 40 electron volts energy, and in electron mode we can detect from minus, that is minus because these are electrons, but from 0 to 75 electron volts energy. We do this in high resolution. Again, I'll tell you why we do this in high resolution, and these are the plasma parameters which you can actually measure. I am assuming that you are already aware of what I mean by plasma. A plasma basically is a thermalized, I am giving you a very colloquial definition, not a textbook definition. There is a soup of ions and electrons which are properly thermalized. They follow a distribution, which we all know is called Maxwell-Boltzmann distribution. So whatever energy is there in the system, it is redistributed, continuously exchanged between ions, electrons and neutrals, and you form a thermal system which we call as plasma. So typically the plasma conditions in our lower Earth atmosphere, lower Earth orbit they fall in this range. So we actually can detect such temperatures and densities. When it comes to electrons, if they are properly thermalized electrons, their temperatures will be even 25,000 K is high. They will be less than that. But sometimes a very high energy flux of electrons come from the solar wind itself. Okay, so they can have very high temperatures. You can see here the temperatures can go as high as about 500,000 Kelvin. So our instrument is again capable. Don't worry, when they are at this high temperature, the densities are extremely low. So yes, it does cause damage to the instrument, but it is not substantial. So, so we built this instrument, which I told you, this is called ARIS. These are the two sensors, which we will discuss in detail. This is the whole team with our director and our chancellor, Dr. B. N. Suresh, and ISRO chairman and our registrar. So this whole team of 4 faculty and students. This is where we actually had this launch in 2019. So I'll come quickly to the instrument now. So in this instrument, I can directly go to the instrument. The instrument works like this. Imagine you have a cylindrical, this is a cross section. You can say this is a cross section. There is a plate. You can see this object is a metal plate. We call it a collector. And in front of this collector, we have metal, perforated metal mesh. So these are metal plates with holes. When we want to detect the ions, obviously, we want the ions to reach to this plate. But plasma contains both ions and electrons. And if both ions and electrons go to the collector, then you will not basically measure a current, because positive ions will be compensated by almost the equal number of negative charges, and then you will not get any current. So to be able to do that, the first thing we do is we put an electron retarding grid here. So when the electrons try to enter into this box, they will get repelled. Of course, that depends on what energy electrons get repelled is based on the voltage which we apply to this electron retarding grid. Then comes the ion retarding grid, and then secondary electron retarding or electron suppression grid, and then the ions get collected on the collector. Now, when you say voltage, okay, and this is universal, voltage by itself has no meaning. Voltage, you cannot simply, somebody says, okay, apply 10 volts. It is meaningless statement as far as electrostatics is concerned. You have to define a reference. Without a reference, that voltage means nothing. Okay. So the voltage, for example, when in the lab you say apply 5 volts or 15 volts to bias an IC, you are basically inherently, implicitly imply that it is with respect to the lab ground, which is considered as 0 volts. That is your reference. With respect to that, you apply whatever voltage you apply. Okay. So, but when you have a spacecraft, the spacecraft is floating in space. It doesn't have an earthing point. So then, how do you define a ground? So, whenever you run a power supply must complete a circuit. So the spacecraft itself, its body, metallic body, is connected to one pole of the power supply, and the other polarity of the power supply is used to drive the electronics. So here also, we connect this other end of these voltages to the ground, the spacecraft ground. But there is a problem. Your spacecraft is not sitting in vacuum. Your spacecraft is sitting in vacuum conventionally, but in the presence of plasma. And plasma itself has its own potential. That's called plasma potential. So when you suspend your spacecraft, a satellite, into this plasma, the surface of the satellite, metallic surface of the satellite, will acquire plasma potential. So therefore, the first grid, if you see, is not connected to any polarity. So this first grid comes in contact with the plasma. The plasma is on this side. The first grid gets plasma potential, and the spacecraft ground, which is pointed here, also gets the plasma ground, the plasma potential. So the voltages which we are applying, they are with respect to this potential. So this potential is negative. It will repel the electrons. So if from the plasma, if the electrons try to enter, up to the electrons with energy equivalent to V1 will get repelled out. We typically apply -5 volts, which generally takes care of this energy electrons. Most of the electrons will be repelled out. Then the next one is basically ion retarding grid. So imagine a situation that an ion with energy 10 electron volts is entering into your RPA. If I apply 5 volts, 6 volts, 7 volts, the ion will still be able to cross and hit the collector. So you will get full current. But the moment this voltage crosses plus 10 volts, this ion will be repelled back. So if I plot a graph of the current on the collector as a function of this retarding voltage, I will get a step function. But you get that step function because you assume that only one energy ion is coming. Imagine if you have a group of ions coming with different energy. Then the shape of that step will get modified depending upon what are the constituent ions and what is their energy distribution. So this is how basically a retarding potential analyzer works. The scan of this voltage, okay, is used on the x-axis, and on the y-axis we plot the collected current. Now, what happens usually is that all this works as far as electrons and ions are concerned, but when there is UV radiation or extreme UV radiation, obviously that UV radiation doesn't get affected by electric field or magnetic field. So it can go straight and hit this electrode. Once it hits the electrode, it can eject an electron by photoelectric process. That electron will go back to the space and you will get positive current, because one electron is lost, so you get positive current. But the problem with that is that was not an ion. You didn't detect an ion. It was actually a UV radiation. So because such events can occur, what we do is we have another negatively biased grid here. What this grid does is, if any such secondary electrons are emitted from this collector, because of this negative potential, they are pushed back to the collector and they reduce the amount of error in the current which you measure. When it comes to electron RPA, just reverse the polarities. The first grid here was negative with respect to the plasma potential. You make it positive with respect to plasma potential. And instead of ion retarding grid, now you have electron retarding grid. And do the scan again. And again, we have the ion suppression grid, and so on. So there is a direct similarity between the two structures. Actually, this one is not really required because we already have this as a negative voltage. Any secondary electron will anyway be pushed back onto the collector. Now, once this is done, imagine now I know that you come from very diverse background, but I will be assuming that you already know, because you are studying atmospheric sciences, you already know that when we say a gas at a certain temperature, it has a certain velocity distribution. So there are these ions and these atoms and molecules in a gas, they move randomly in random directions with a velocity distribution which can be very accurately connected to their temperature. So this is fine. So what will happen if you are keeping one of your instrument like this and there is gas here? Some particles which are randomly moving in all directions, some of them can enter into your detector, and if they have charge like ions or electrons, they will get detected. So this is what normally should happen if your instrument is sitting in the lab or it is sitting stationary. But for the satellite, if this instrument is on satellite, and if the satellite has to stay in orbit, then it has to move. And if it moves, then if you are sitting inside this probe, in your frame of reference, the ions will move faster towards you because you are going in that direction. You can imagine, usually the RPA is mounted in the same direction as the velocity direction. So this direction will be the velocity direction. So as the spacecraft moves, it starts gobbling up the ions. So in the frame of the reference of this sensor, the ions are coming with higher velocity. Okay. Now, because there is a spacecraft velocity is fixed, but ions can have different masses, so they get different kinetic energies based on their mass. But this instrument is an energy analyzer. So when it does energy analysis, depending upon the masses of the ions, the current can stop at different energy values. So in principle, if your RPA is mounted on a spacecraft, not only that you can measure their energy distribution, you can even identify what mass ions are these. Are these oxygen ions, nitrogen ions, hydrogen, helium, what species are there? That also we can actually detect. And we do this, actually we can detect it. Now, as far as electrons are concerned, unfortunately electrons are too light compared to ions. So they move very fast. So the spacecraft velocity does not affect the electron energy distribution very significantly. So we don't do such velocity corrections to the electrons, but the ions, we follow a very complex velocity correction. This expression is a standard expression for retarding potential analyzer mounted on a spacecraft. Here I have assumed the spacecraft velocity to be 7,600 meters per second. That was our experimental velocity. This is the effective area of our sensor. This is the total area of our sensor, sorry. Eta is the transmission efficiency of the sensor. I'll show you, because you have this grid here, right? So it has holes. So some parts it is blank, some parts are shadowed. So you don't get, even if the opening has a certain area A, the sensor does not see the full area. There is a reduction, and that reduction is given here by a factor which is less than 1. Small v is the velocity of the spacecraft. This Vs is the spacecraft potential. What is the spacecraft potential? As I said, plasma has its own potential, so the spacecraft gets charged. So whenever charged particles enter into your sensor, they get affected by this voltage. So you have to correct for it. So this is how we actually correct for it. And this is how the expression looks. Now, if I take a typical situation, this is one typical situation I want to show you. Suppose you take oxygen ion, helium ion. This is for helium ion. So the helium ion coming from a plasma which has very low temperature, extremely low. This kind of plasma doesn't actually exist easily. So let us say 20 Kelvin plasma. It's very low plasma. Okay, and it's a hypothetical situation. Say 0 Kelvin plasma. Okay, we should assume that it is there. So practically such a thing cannot exist. This is only theoretical plan. Okay, so what will happen as you change the retarding potential on your sensor? You can see that you are receiving a very high current. Okay, and suddenly at some potential this will drop to 0. This potential corresponds to the effect of temperature as well as the spacecraft velocity. So if we use this formula, we will be able to get the temperature. If you fit this formula, you will be able to get the temperature of the corresponding species, and that's what we actually do. So we have a code which does this fitting. So this is at 200 Kelvin, this is at 20 Kelvin. Similar thing if I do, this calculation was done for Venus, not for Earth. We did this because Earth's ionosphere mostly contains oxygen, as you will see in our data. So it's not very fun, much of fun to do this analysis, but the ionosphere of Venus contains many different species. So you can see the heaviest, the lightest species giving you step first, then the next lightest, then the next, then the next, the next. Okay, and this knee which you see, the shape of this is related to the temperature of the species. So you can actually measure the plasma temperature species by species, and that has a great implication to the dynamics in the ionosphere. So this is how we normally do the calculations. These are only calculations, these are not simulations. But of course, calculations are not sufficient because they assume idealistic conditions. For example, when we did this, applied this formula, we assumed that this potential, this is the applied potential we applied. This potential is exactly what you apply is what the ions will see. But in reality, we use metal mesh. So metal mesh like this has holes, and these holes will distort the electric field seen by the charged particles. So that has an effect, and very strong effect on the measurement process. And that requires a lot of simulation. So we do these simulations. I will not get into the details. We use a commercial software for electrostatic simulations. It is called Simion. Part of the simulations are done using Simion, and then we actually fabricate these. These are very fine mesh, microscopic mesh, which is mounted on metallic ring for structural rigidity. What you see on the left-hand side are nickel grid. They are imported. They are very fine and electroformed using an electroform process. They are made. This was a big problem for us because they are extremely sensitive, very expensive, and alignment becomes a problem because they're extremely very fine mesh. So we optimized our simulations, and we actually designed our own geometry, and this geometry was fabricated in Bombay using laser cut microscopic laser machining technology, and we could get very good quality mesh prepared. This is what we used in our first mission. In our second mission, we will be using this. This is already ready. The second mission, the hardware is already prepared. Now, No matter whether you use nickel or stainless steel, you're talking about very low energy. As you can see on the x-axis, we're talking about few volts. This is very low energy. When you're dealing with very low energy ions, it's always a problem because some dust particles sitting on this mesh or some part of this metal is slightly oxidized, there will be charge accumulation, and that charge accumulation will destroy the uniformity of the electric field. So what we do is we actually coat this mesh with gold. So this is what you will see here. This gold coating is also done at IIST. So we coat this thing with gold, gold being the very high conductivity and extremely low reactivity material. It doesn't get oxidized and it conducts very nicely. So we can get more uniform electric fields. This is how we prepare the mesh. Okay. Then once the mesh are prepared, this is our mechanical block inside which this mesh are put. From the front, there is an opening for the ions and electrons to enter. We stack our grids. These grids are separated from each other by Teflon rings. Teflon rings separate them from each other. In the spacecraft, we use Tecapeak rings. In the lab, we use Teflon rings. And then that is stacked together. And then this is the assembly process. You can see the various parts kept there, and we have the jig on which we do this assembly. And this is all done in-house. Okay, everything is assembled at IIST. We do this in-house. Okay, now comes that you have made this. Fine, you made this box. Okay, now comes the question, because you're going to spend a lot of money to launch it. Every kilogram of material you launch in space, you pay $20,000. We don't have to pay because Indian space program has this very good aspect that Indian Space Agency launches any payload from an Indian educational institution for free of cost. Moreover, since we are part of Department of Space, we can get these opportunities without actually, specially paying for it. Of course, if we are not paying, that doesn't mean the launch is free, because somebody has to pay for it. So government pays for it. So we have to be extremely careful what we launch, and it should work. It should do what it is supposed to do. So for that, a large number of tests are done on the mechanical, electrical, thermal, and the physics aspects of the sensor. It should withstand the mechanical vibrations and shocks. It should withstand the thermal shocks. It should withstand electrical disturbances, and it should perform. And at the end, it should give you the scientific data which you expect from it. Now, you can't simply get guesswork, because just because you did the simulation very, very well, just because you did the calculation very well, doesn't mean it will give you good quality data. You need to do tests in the lab, and the review process of Indian Space Research Program is extremely complex and extremely stringent. Unless you pass those tests, you won't be able to put this box on any satellite. Okay, so we have to also demonstrate that. Now, demonstrating this at such a low energy is an extremely challenging task in the lab, because to produce ion beams of this energy range is not very difficult. What is difficult is to know that you have produced them with this much energy. Generally, high energy ions are easy to sense, easy to detect, easy to analyze, and you can tell, yes, I have produced 200 eV, 500 eV proton or 500 eV oxygen ion. You can do that. But when it comes down to 1 or 2 or 3 electron volts energy, then even the smallest amount of dust or contamination in your vacuum chamber will simply distract the ions because their energy is too low. So then it becomes a challenge to know what you have produced. So as I said, it is very easy to produce low energy ions. Problem is to know what is their energy. And for such performance of an instrument, you would need to know how much energy is produced. So we built a very interesting system, a calibration system. So this is a calibration system. This instrument, this is the design. I'll show you the photograph of the instrument also in the next slide. So basically we have an ion source sitting here. Then there are lenses to focus the ion beams coming out of this ion source. And then we have a device here which is called parallel plate analyzer. It is basically the top plate is grounded, the bottom plate is given positive voltage, and as the ions enter into this box, depending upon the voltage applied to this, they bend. And you can actually do very good calculation, very simple calculation. Maybe many of you have already done this in your +2, that this electric field will bend the ions onto a trajectory and it will go and hit this plate somewhere, depending upon the voltage applied and the energy of the charge particle. Now, we make a hole at a specific place. We call it range. This is the entrance hole. This is the exit hole. The ions enter, and if they have the right energy and this voltage is right, they will go through this hole, and inside this brown box is where we keep our retarding potential analyzer prototype. Okay, and then we know, knowing this voltage, we know what energy ions we are sending, and we know that very accurately. We can find that energy of the ions with an accuracy better than 1%. That energy ions are entering into this RPA, and then we again do, because RPA, as you saw, does energy analysis. So we do energy analysis again, and we try to match our results and see how our RPA is behaving, whether it is giving us the desired results or not. So this is the SIM-ion simulation for the same. The ions enter into the parallel plate analyzer, and depending upon the correctness of their energy and the voltage applied, they bend into a parabolic path. Oh, sorry, my mistake. This is opposite. This is okay. This is reflected. This is where the source sits. The ions enter from here, and then the correct energy ions come out, and the RPA sits here. So this is just one simulation. There are several simulations. So this is the actual mechanical drawing. You ignore this in between part. This is, again, we are trying to do something interesting, but I'll not discuss that today. So this is how the mechanical structure looks. So our ion source sits here, and the ions enter. Inside this is this structure, which is made from stainless steel, and then the ions get deflected, and the RPA sits here in this cavity. Of course, you can't do these experiments in air. You will have to do them in vacuum chambers. So we have 2 vacuum facilities at IST. Both are, again, I'm very proud to say, these are all designed by our students. These are not commercial facilities. These are designed by our students, and then they are fabricated as per our drawings. Even the mechanical drawings, the actual flow drawings are provided by our designers to the vendor. Of course, we can't do the cutting and welding and all these processes and polishing. That is done by commercial vendors, but these full information, full design is provided by us to the vendor. Usually a turnkey facility, if you want to build something like this big one, this is quite big actually, a human can stand here. This big facility will cost you anywhere between 2 to 3 crore. We could build this in 56 lakh. We don't buy the ready-made facility. We buy the components. We design the components ourselves. We do this. I'll come back to this facility in a few minutes. This instrument is tested in a smaller chamber. In this chamber, we test the experiments with only ion beam, and we create vacuum in this chamber. This is a 0.5 meter class chamber, and we produce the ions of argon, because argon is an inert gas, easy to produce, easy to ionize. Oxygen or nitrogen, if you produce inside the ion source, they will produce oxides and nitrides due to high temperature, and it can damage the ion source very quickly. So we do all these tests in argon environment. So the pressure inside the vacuum chamber is kept at something like 10 to the power minus 5 torr, and we work at that pressure typically when we are operating. Otherwise, it can go up to 10 to the power minus 7 torr. So when we do these experiments with ion beam, we use this facility. Okay, but then comes a question. You are not going to get a very nice and focused ion beam from the source when you launch the instrument in space. In space, the spacecraft is going to be submerged in plasma, and you need plasma. Without plasma, you cannot fully qualify this instrument. Now, traditionally, ISRO has launched similar instruments, not exactly, RPA has been launched long back, a simpler version of that. Langmuir probe and a lot of other plasma probes have been launched. The problem is you can't test them in plasma conditions. That was the situation. So usually people used to do tests with such kind of ion sources or some other sources, and then with conventional wisdom, calculations, simulations, people used to declare, okay, let us do the experiment and see what happens in space. They used to be meticulous, very careful, learn from others' experiences and do. But at the end of the day, there was no plasma facility for testing the payloads. So what we did at IIST is we wanted such a facility, and we didn't want to get into just doing the calculation and simulation and declare that our payload will work. So we built a facility inside this chamber. It is called a back diffusion plasma source. So I will show you the video of that. We can fill this whole chamber with argon plasma, having plasma characteristics similar to lower Earth orbit. And for payload testing in plasma environment, this is the only facility right now in the world, sorry, not in the world, in the country. This is the only facility where you can actually produce. There are many plasma chambers in the country for different purposes. Okay, because the plasma conditions can be very low temperature to very high temperature. There are very widely ranging conditions, widely ranging densities, and very widely ranging purposes. This one is for lower Earth orbit plasma simulation. So this chamber is the only facility. If you want to test it, then you can test it here, and I will quickly show you a video of how we can actually fill the whole 1.5 meter chamber in plasma. So just for a minute, I will share another screen with you. This is not the best one. This one. Okay. So I share my screen. Can you see a video?
Yes, sir.
Yeah. So this is a view from the one of the viewports of the vacuum chamber, that large vacuum chamber. Some instruments are mounted inside, and this whole thing, what you see, is in vacuum. Okay, and you can see a bluish glow now in the chamber. That glow is basically the full chamber is filled with argon plasma. Now it is off. Now it is on. So you can fill the whole chamber with the plasma, and not just fill the whole chamber with the plasma. That's not all what we do. We also have some home-built sensors which we use to characterize that plasma also, so that we know what plasma condition and corresponding to which altitude and which condition we are subjecting our payload to. And then our payload does the electron and ion RPA measurements, and we can acquire that data. So this is how this thing works. There are lots of details we can discuss if you are interested. I do not know what sort of background you do. If you do this kind of work, I can share more details. I can share contact details of our electronics and mechanical experts who actually, the faculty from other departments who actually designed these things. I am just a science person. I am just involved in the science side, but the actual design work, a lot of inputs come. And they are, I can give you their details and you can consult them. They are really good in what they do. So they will really be able to help you if you are interested in such endeavors. Now, this is the cut view of the sensor package. The one of the RPA is for electron, another one for ions. And this is the cut view. You can see these are the grids. Okay. I am going to talk a little bit about the electronics arrangement here. So as I showed you some time back, this is the first grid, which is floating grid, which is supposed to float to the potential where the plasma potential of the space plasma is. And then there is an electron repelling grid, then ion retarding grid, then secondary electron suppression grid, and then there is a collector. This collector will give you the current, and that has to be measured as a function of voltage applied to the ion grid. Now all these things, of course, you want to do automatic and fully in closed loop condition by itself, you want it to do. So our people came up with very intelligent ideas. For example, if you look at the specification in the beginning I showed you, look at the numbers and you will realize the challenges. Look at the numbers. We are talking about 10 to the power 2 to 10 to the power 6 centimeter cube of ion density and even larger range of electron density. So we are talking about here 4 orders of magnitude changes. We are talking about measuring picoamperes of current capability. So when you're trying to measure picoamperes of current, it's extremely difficult, because if you just move your hands, if you just wash your hair and don't put oil, just wash your hair, and dry hair, you move your hand, and then you move your hand across a metallic electrode, you will induce nanoamperes of current. So when you're trying to measure picoamperes of current, it's an extremely difficult task. Moreover, you're going to do that in a plasma environment on a spacecraft which is not grounded properly. So it becomes a big challenge how we actually do this. So for that, our electronics guys, our avionics faculty, 2 of them, they came up with very intelligent mechanism to do this. Again, if you are interested, I can tell you how conventional mechanisms also follow, give you that kind of dynamic range, but then they use a log amplifier, which actually reduces the finer variations in the current because of taking the log. Our data comes in linear fashion, and a very intelligent algorithm is implemented that we can actually do it over the full dynamic range. So the 2 RPAs are, this is just a block diagram to show that the 2 RPAs are how they are integrated with the rest of the electronic block, but I think I'm already sort of going too much beyond my time, so I will go ahead. Again, if you're interested, I can point you to the right faculty who actually has designed this, and you can consult them. So this is where the very important aspect of the measurement comes. This is a front-end instrument, basically a current detector or current to voltage converter, which sits right below the collector. So the collector is here. That PCB sits right here, and a very fine, very small wires, very small length wire, just a 1 centimeter or 1.5 centimeter wire goes from here to here, so that it doesn't pick up noise, because after all you're trying to collect picoamperes of current. And then a very high sensitivity amplifier is used here, and that is converted into voltage, and then that is given to the second board. This is our main board. The main everything is done on this board. This is the main controller which sits here. We have the power unit here, the power block here, and this is the signal processing block where the amplified signal from the sensor comes. It is processed, and also the ramp is generated here because we want to do a voltage scan. Because if you remember, we have to scan the RPA retarding grid, and this scan has to happen within a second. So you have to go from 0 to say 15 volts in 1 second or 2 seconds. So this ramp also has to be generated on board. So all these things are generated on this single board. Again, I'm very proud to say this is a design of our faculties from avionics department, their ideas, their design, implemented by students. This was even the layout was designed by them. It was given to a fabricator outside, and then the PCB was fabricated. The population of components was done by IISU and VSSC teams, and of course their help was involved in designing this. In fact, it was reviewed by VSSC team thoroughly, and it beautifully worked. Another aspect, when you send something so expensive to space, you have to really spend a lot of money on the components, and those components are called space grade components or space qualified components. For example, a 555 timer which you buy in a market for say 5 rupees, if you want to get a space grade version of the same, it can anywhere cost you say 5 lakh, 10 lakh, because of the processes by which it is qualified to go for space application. Here, since we were just doing our experiment for a short period of time, we could discuss with ISRO teams, and we requested that we would use commercial off-the-shelf components, and they were also keen to know whether commercial off-the-shelf components will work to our satisfaction. So all these things which you see, practically all of them, except a couple of the components, practically all of them are actually commercial off-the-shelf components bought online actually, and then populated the PCB, and they work beautifully for 2 months. After 2 months also, it should be working, but the telemetry from the PS4 stage did not work, so we could not confirm beyond that. And since this was an experiment, we could actually manage that. This is how the full integrated box looks like. The sensor is sitting here with the front end electronics. This is the processing electronics sitting on the bottom module. And then these two modules are sandwiched. Once they are sandwiched, where to place them on a spacecraft? So we have to do a very special type of simulation to identify how the plasma in the space is affecting the spacecraft and identify the location. And I'll not get into that. Of course, when you make this box, you have to make sure that it will survive the launch vibrations. So we do mechanical simulations also for the launch simulations. Then thermal, because again in space it is in vacuum, good vacuum. So thermal stresses will destroy electronics easily. So you have to make sure that you don't stress it too much that they start having faults. So we do thermal simulation also before we do the final fabrication. After all this, again, it's fine. You have done all the simulations. You have to demonstrate that the simulations are correct. So what we do, these are the photographs taken at the VSSC facility. So what you see on this side is a thermovac chamber. Inside a vacuum chamber, we actually create the vacuum, and then this black portion contains lots of halogen lamps, and we stick lots of thermocouples on the body, and we try to achieve the same temperatures from very low temperature. This contains liquid nitrogen flow also. So we can go from extremely low temperatures to very high temperatures and make sure that the sensor works at those temperatures also. This is a thermal test. Then we bias the electronics and we keep it on a table, this kind of table, vibration table, and we vibrate it to those frequencies which are expected to be experienced by the box when it is being launched. So we actually subjected this and made sure that our signals are coming fine. Everything, when everything is passed and the quality control department has cleared that we have done our job well, then only you get to see this situation where this is the PSLV top section where the main satellite, this was a DRDO satellite which was mounted. Then these are some smaller satellites, and our payload was sitting on this deck. This is called the PS4. This is a PS4 stage, and this stage, this sensor, our Ares sensor is mounted here. Now normally rocket goes upwards like this, and I told you that RPA should be mounted in the forward moving direction. So the peculiarity of this mission was this satellite was to be injected in 750 kilometers orbit. Then these smaller satellites were to be injected at a lower orbit. So in space, this stage was supposed to first go to 750 kilometers, eject this, and then reverse the direction, and then come down to 550 kilometers orbit. So because of that, we were actually facing in the correct direction. So this is the mechanical drawing. This is how actually it was mounted. This is where Ares was mounted in the actual launch platform. And this is the first set of signals we got. It was a great moment for us. All our students, faculty, they were really ecstatic that we got this in our first attempt. And this was launched on 1st April 2019. It was really launched, okay? Don't go by 1st April date. And we actually got this data by evening after a few hours when this was switched on. This stage is not a satellite. This is just a stage which normally used to be just wasted. It will just keep revolving around the lower Earth orbit and finally re-enter the atmosphere and burn. But ISRO has done something really clever, that this has now been offered as an experimental platform for people like us, so that we can actually build small payloads and test them. It's a very cheap solution, a very efficient solution, and we can do lots of experiments without bothering about the communication and stabilization and onboard computation. Everything is taken care by this stage. So this is one advantage, and many people are now planning, many colleges are planning experiments on PS4 already. So this is how the data pattern looks. I will not get into it, but if again any of you are interested, we can discuss this. And then we start getting the first set of data. Of course, this data is coded data. We have a very special algorithm to compress the dynamic range. So this is not fully converted into the right ranges. We do that thing. I'll again skip how we process that data. I'll directly show you the results. So I'll just spend a few minutes on this before I stop. So on the x-axis, we have the Indian Standard Time in hours. So you can see this is the morning time between 8 o'clock to 12 noon. And this is the evening time. This is 20 hours, that is 8 o'clock in the evening and midnight. These in-between points are not to be considered. They were taken from another station near Antarctica, and the time conversion is not the correct one. So that's why I have marked them separately. These are taken over the Indian subcontinent and say Mauritius and so on, those places this data was received. You can see this is the spacecraft potential. You can see the spacecraft potential is positive here in the daytime and negative in the night time. Again, very interesting effect, because in the daytime the solar UV radiation will produce a photoelectric effect and your spacecraft will basically get positively charged. In the night you don't have the UV flux, but your spacecraft is still floating in plasma, so it accumulates electrons and gets negatively charged. Then this is the ion number density, the density of ions. As you can see, in the daytime you have very high ion density, because obviously there is a solar flux, high energy flux coming, producing higher density of plasma, so you will have higher flux density. But in the night you have very low flux density, but it is not zero. Okay, it is low, almost order of magnitude, 1 order of magnitude less flux density we measure on the night side. So this is the day side, this is the night side, and it tells you that how the dynamics is. And then of course there are a lot of dynamic models, how the plasma moves from the day side to night side, whether that is sufficient to replenish the decrease, to what extent, all these mechanisms can be studied. Then same situation with ion temperatures. You can see the ion temperature is very high in the daytime, but in the night time the ion temperatures decrease. Again, the same reason, that you don't have the solar flux and you don't have the energy pumping mechanism active right above you, but still there is a flux of density energy coming from the other side of the Earth. And since the magnetic field lines are trapping the full plasma around the Earth's ionosphere, there is a flow of energy, there is a flow of plasma from the day side to night side, and you can actually assess that. This is the data over more than 800 orbits, which I have plotted here. Before I stop, I'll just quickly show you why this kind of measurement should be of any use to us. Is it only academic interest, or it does something more than that? Okay, so this is actually related to space weather. Now, space weather, when it comes, there are many aspects of space weather. Ionospheric aspect does affect us to some extent, in a sense that when we are using satellites for communication, the communication frequencies do get affected by the ionospheric plasma. But we don't care. We basically have several noise rejection algorithms, and the data still comes to you. But when it comes to navigation payloads or navigation satellites also stay at around 35,000–36,000 kilometers from Earth. So their navigation signals pass through this plasma environment, and plasma, just like any other material, has a refractive index and scattering processes. So these scattering processes and refractive processes will actually affect the time scales of reception of these navigation signals, and that effect is very small and it can be corrected. People have been correcting it for. Okay, assuming some sort of average plasma behavior, it can be corrected. Okay, but if I want to really understand these effects, I should know in real time what this space weather is. So this is another very interesting aspect of space weather, which one would like to study using such instruments. So our hope is that with the help of many of students, we will be able to miniaturize this box even further down, and at any given time have not just one ARIS but multiple ARIS going around the Earth and in real time providing space weather information in the lower Earth orbit. So, well, you have remote sensing satellites giving you imagery, and in fact nowadays companies are talking about 24 hours image access to a given location on Earth. So we should be able to do something similar to our ionosphere. Not necessarily every point of ionosphere be covered, but at least in real time. Say, for example, at present, right now, no RPA-like sensor is going around the Earth to tell you what is happening in the ionosphere. Not that it is an alarming situation. If it was, scientists would have put several such sensors by now. But I'm sure that availability of cheap platforms like, say, this PS4 is actually a useless stage in principle. In principle, it is a useless stage. But we have now been able to use it for such purposes. So we plan to do more such measurements using ARIES around Earth. But if you noticed, the logo has blue dot and blue ring. That is because it is around Earth. When it goes around Mars, it will be red. Around Venus, it is orange, and so on. We already have a sanctioned payload for the next Venus mission from ISRO. We are preparing for the payload. Of course, since it is an interplanetary payload, we will be extremely careful, and we will not use COTS components. We will use space grade components, which takes its own time and redesign and so on. It will go on. We will try to reduce the weight because, again, it's very expensive to launch every kilogram to space. We also have a proposal which is in principle approved, but no funding is sanctioned because ISRO also has to take some decisions on that, the mission itself. But the next Mars mission also we plan to take this sensor with slight modifications. We will be implementing it for the Mars mission as well. So we hope that in few years time, we will be having our ARIES design heritage, providing live data around Earth about the space weather, at the same time providing very useful data from Mars and Venus missions. So with this, I would like to stop for today, and any questions on so far whatever we have discussed, we can talk about. Thank you.
Thank you, sir. Thank you, sir. Thank you, sir, for the well explanation about the ARIES mission. We are waiting for more exciting results from the ARIES, and we are wishing all the best for the coming projects also, sir.
Thank you.
So in the chat section, we are not seeing no more questions.
Sorry.
There's no questions till. There's no questions
Okay.
from participants, sir.
Okay. Fine.
Chandrasekhar, sir.
Okay. Thank you.
Can I ask one question, please?
Yeah, please.
We have ionospheric observations with the second talk by Amit Kumar Patra, the director of IATM. So he has shown the plasma irregularities, field aligned plasma irregularities. Can we use such type of observation? Can be corroborated with your observations and can tell something?
Yes, very much. That's actually, one of my student, he is actually an NARL PhD student. So he is also he also uses these kind of radar reflection, radio wave reflections for the plasma assessment, and he is trying to just out of his interest, he is trying to use ARIES data and trying to see the correlation between the two. We are trying to do that, yes. But since the ARIES data was only for 2 months, we have to make sure that at the same time we have some data taken with the ground-based facilities also, so that we can do a positive correlation.
Yeah,
so,
according to your ARIES data, so those days, if that radar is operated, we can see the vertical structure of those ionospheric structures.
Yes.
Like his necklace echoes, he has told at 150 kilometers necklace echoes. So during the I think diurnal variability, I think that could be a great study. We can confirm this spatial observation of your sensor. Great.
Sure.
Thank you.
Thank you.
Thank you all for your kind attention. So we will be back tomorrow morning at 10 a.m. Thank you all.
Thanks a lot. Sign out. Signing out. Thank you.
result.